Hi, Raj.
Hey Pete, how are you today?
Great. You're going to teach us a little bit about combustion analysis in Simcenter Testlab?
Yes, I would like to do that with your help.
All right, sounds great.
Shall we get started?
Yeah.
Okay, good. Hello everybody, welcome to this webinar on Simcenter Testlab combustion analysis. My name is Raj and I'm in the support team supporting Simcenter Testlab and the Status hardware. Pete, you want to tell a little bit about yourself?
And I'm Pete. I'm an application engineer supporting Simcenter Testlab as well.
Excellent. So today we are going to talk about combustion analysis, the importance of combustion analysis and how to do this combustion analysis in Testlab. So here is the agenda. First, I'm going to show a couple of slides on combustion analysis, what is the need for it and what is its importance. Then we'll see how the combustion analysis is done in Simcenter Testlab. And we'll see that there are a couple of different items available in there called TDC determination and combustion metrics calculation. Those are in the Simcenter Testlab combustion analysis module. And we will wrap up with some final thoughts.
And the purpose of doing combustion analysis for some of our users is not so much to be a combustion analyzer, but to maybe understand the trade-offs between noise and vibration performance versus the efficiency of an engine if they're messing around with combustion. Is that right, Raj?
Yes, that's correct. So the tools in Testlab are to enhance, allow you to do this combustion noise calculations or combustion metrics calculation simultaneously with the typical NVH metrics calculation. For example, from the data, you may do some overall levels or RMS levels from the microphone and the accelerometer data. So the objective is, if the interest is in doing the combustion metrics calculation simultaneously with this typical NVH metrics calculation, then you can use this module of Testlab called Simcenter Testlab combustion analysis.
Yeah, so if we change our pilot ignition or fuel injection timing, we can understand how that affects noise, vibration, as well as combustion efficiency like IMEP, etc.
Yes, that's a good point, Pete. Yes. If you have one system that does both in terms of NVH metrics calculation as well as combustion metrics calculation, I think that will be really helpful in terms of making design decisions, check the effectiveness of certain combustion countermeasure, as well as to understand what is the trade-off of doing that. So, for example, if you make one change in the combustion mechanism, let's say you change the peak cylinder pressure or you change how a pilot injection for fuel injection, how does that help, or the angular position in terms of the injection timing. So what is the trade-off between combustion metrics like IMEP, PMEP, net mean effective pressure, versus what do we see in terms of overall level noise or certain orders? The other thing is also sometimes you will see when you're doing the combustion or when the engine is going through combustion, you'll see that there can be variation from cycle to cycle. So to really understand how the performance is changing from cycle to cycle and what is its effects on the general vibration and acoustic behavior, then you really need to look at even the noise in cycle by cycle basis. That will give you some valuable insight into effectiveness of certain combustion schemes and will help you better tune the engine for finding a sweet spot for combustion metrics as well as the NVH.
So we don't want to depend on just a single cycle for our analysis because there's a little bit of variations in the combustion cycles or cycle to cycle. So that's why we want to look at a whole bunch of cycles or cycle per cycle.
Right, exactly. So let's go to the next. What do we do in combustion analysis? You will notice that in combustion analysis, one of the key requirements is that you measure the cylinder pressure. And cylinder pressure you can measure by using a cylinder pressure transducer. There's like a pressure sensor inside this cylinder, and you will also be simultaneously be capturing the volume of air that is present in this as it goes through the different parts of this cycle. Inside a cylinder, there is this piston which moves up and down. So the volume of air changes, which is shown by this blue curve here. And correspondingly, the cylinder pressure also changes, which is shown by this green curve here. And how this pressure changes as a function of this volume. So PV, pressure volume, that is plotted in a PV diagram. And that's what you see in this right-hand side. Here you will see the y-axis is the pressure and the x-axis is volume, and they are being shown in a log scale. once you have this PV diagram, there is a lot of different combustion metrics that can be calculated. So first of all, to understand this PV diagram, if you take a typical 4-stroke engine, like you have intake stroke, there is a compression stroke, power stroke, and then the exhaust stroke. In the bottom part of this PV diagram, you see this intake, and then goes through compression, then goes through the power stroke, and then finally comes back to complete the exhaust stroke. So these are 4 strokes in a 4-stroke engine. Using this PV diagram, you can calculate certain metrics like the indicated mean effective pressure, IMEP, or PMEP, pumping mean effective pressure. IMEP represents the total amount of work done by the engine, like the thermodynamic work. If you divide that over by the swept volume, you get a mean pressure, and that is the indicated mean effective pressure. Now the PMEP, on the other hand, the pumping mean effective pressure, that represents like the amount of losses that happens due to the pumping effects. And so you want to have that at a minimum, and you want to have this IMEP higher. The difference between these two, that is IMEP minus PMEP, that gives the net mean effective pressure, NMEP. So we'll see how to do these calculations using Testlab.
In the ideal world, we'd love red to be 0 and green to be everything. Then we'd have great.
Right. Yes, exactly. That's the objective, but there'll always be some losses. So you try to just achieve for minimizing that while trying to maximize this IMEP. So we see that one of the key requirements for combustion analysis is the cylinder pressure measurement. And you notice that this cylinder pressure is being shown as a function of cycle or angle, like the angular position. Measurement of this angle is also very important. So to be able to do this combustion analysis, we have to measure the cylinder pressure, and we have to measure this angular position of the crankshaft. So a typical measurement will involve, for the angular position, you need some kind of pulse measurement for involving multiple pulses per revolution. So you can mount like a magnetic pickup sensor, for example, on a flywheel to get these multiple pulses per revolution. That is a 60 ppr, 60 pulses per revolution example. In addition, you will need a 1 pulse per revolution signal that is used for zero referencing or TDC determination. So that is for absolute determination of the top dead center, or for zero referencing, we call it. So you need that also. So you need multi pulses per revolution as well as a single pulse per rev.
TDC is top dead center.
Yes.
Okay. And of course, we acquire data in the time domain. It's very important to have an accurate tachometer or high pulses per rev so that we can transform the data from time to angle. Is that?
Yes.
That's what we're going to use this for in order to do this combustion analysis.
That's right, Pete. That's an excellent point. We will be measuring data with respect to time, but we need to convert that to angle so that we can get the pressure and the volume in terms of the angle. Sometimes you will see that on some gear tooth profile, you will have a missing pulse. You can use that for referencing also. And you will see some situations where there are 36 pulses per rev with 1 missing pulse. And that missing pulse could be used for the zero referencing also. So you need the multi-pulses per rev and the 1 pulse per rev for zero referencing. You can do both of those measurements using an incremental encoder. This incremental encoder gives really fine resolution in terms of the number of pulses. So they have very high count for the pulses per revolution. And they also produce 1 pulse per rev signal for reference purposes.
Yeah, and you can use a SCADAS RV4 card with an incremental encoder.
Yes, correct.
It's got a specialized input for those.
Yeah. So if you think about, like, from a high level, what is the process involved to do the combustion analysis in Testlab? You do the measurement of the cylinder pressure. And if you are measuring multiple cylinder pressures, you will need to do what is called a cylinder alignment to take into account the firing order. So you have to do that. Then the next step is to do the zero referencing or the top dead center determination, TDC determination. And those will be done in our angle domain validation worksheet of Testlab. Once we have done that, then we go to this combustion analysis module where we actually use the information from whatever we develop in the angle domain validation and feed that into this combustion analysis to specify cylinder geometry, as well as to do some corrections on the cylinder pressure to account for the drift, which is called pegging. And finally, once we have a good TDC measurement, top dead center, and we have done pegging, then we can use this data for computing these combustion metrics. That is the overall flow of how things are going to work for combustion analysis. Right, Pete?
That's right, Raj.
Okay, so with that, we see that here that the first steps we do is in the angle domain validation worksheet of Testlab. That is an add-in for doing the angle domain processing in Testlab. So let's take a look at that first. So angle domain analysis in Testlab. Before we jump into the actual software for doing that, first let's take a look at what is the concept involved in this angle domain analysis. Now, typically you will measure vibration or acoustic data as a function of time with a certain fixed sampling rate. So the timing of the samples is fixed and they are equidistant in time. And that's what you see in the top part here. And even cylinder pressure signal that we acquire is sampled as a function of time. But if we measure the tacho pulses coming from the multiple pulses per revolution, for example, the tooth of a flywheel, then you can use that to measure in the tacho channel. It will have the information about the angular position of the crankshaft or the flywheel. And using that, you can develop what is called this angle time relationship. So the original time data will be there, and then you have this angle time relationship. So the data will be transformed from original amplitude versus time to now show it with respect to angle using this angle time relationship. As part of this, the data is resampled to get equal increment of the angular position. Original sampling was done with respect to time, but now after doing this calculation with the adaptive resampling, now the data will be sampled with respect to equal angle increment.
I guess that just makes the analysis easier. If we resampled to 1 degree increments, we know every 360 samples is 1 revolution, huh? Or 720 data points would be like a complete combustion cycle on a 4-stroke.
That's correct, Pete. Yeah, so that is what we want to do, because as we saw earlier, all the combustion metrics, they're calculated with respect to PV, pressure and volume, and they have to be done in terms of the angular position for the correct calculation. So in terms of what is the hardware needed for doing all this in Testlab, we need a SCADIS mobile or a SCADIS recorder or a SCADIS lab. You will connect your sensors. It can be microphone and accelerometer like the ICP sensors, as well as your cylinder pressure. And simultaneously, if you want to measure some strain gauges or for that matter, some torque, you can do load cells. All that you can plug it to the input channels of the SCADIS front end. We will need to measure the RPM, and that is measured as a tacho channel. And once we have all the instrumentation set up, then we can do the transformation of the data from the time domain to the angle domain. When we do the tacho measurements, as we said earlier, we need multi-pulses per rev, can be 60 or 720 or 1024 pulses per rev, as well as 1 pulse per rev, which is used for the zero referencing. There are a lot of different tools available in the angle domain processing that can help us to precisely position where that zero is or how to determine this top dead center, because that is a critical step. The top dead center determination is a critical step for doing combustion analysis. Anything else you want to add, Pete?
No, that sounds good. I'm eager to see the software.
Okay, good. That's the correct cue for me. So let me exit out of this PowerPoint and then I'll go into the Testlab software. So here I have an example data set here for this combustion analysis. Here, what I have done is I have launched Testlab and then I have added in the combustion analysis module. So I went to tools, add-ins, and I added in combustion analysis. This uses 20 tokens, but it has certain prerequisites. And the prerequisites are the angle domain processing, which is 42 tokens. And it also uses signature throughput processing, which is 36 tokens. 42 plus 36, that is 78 plus 20 for the combustion analysis. So that is 98 tokens are needed for this. We need this customized metrics calculator add-in also, but that one does not require any additional tokens. So that is part of the signature throughput processing. It is automatically included. So I have done that, and that's why we see the different worksheets here: time data selection, time data processing, angle domain validation, and combustion analysis. So I have an example data set here I would like to go through to show you how to determine the TDC. In this example data set, what I have is a proximity probe. Like the proximity probe was installed in the spark plug, and we get a voltage signal for that. So if I drag that and drop it into a display here, I'll change the format to real. So this is how it looks like. So it shows the proximity probe as the piston moves up and down inside the cylinder. When the piston reaches the topmost position, that is close to the top dead center, then the voltage will be higher compared to when it's at the bottom position, then the voltage will be low. And that is how this is changing, this proximity probe sensor. We also have the RPM measured from the 1 pulse per rev signal, as well as the multi-pulse per rev. That is, here in this case, this is 36 pulses per rev. And if we look at this RPM signal, it's supposed to be like steady state condition. And we can see the RPM is close to around 700 RPM. There is some fluctuation to it, but it is not like a run-up type of situation where in this case, actually, the RPM is fairly constant. So this one here is the 1 pulse per rev signal. If I show the multi-pulse per rev, so that is a 36 pulses per rev with one missing pulse. That is 36 minus 1 pulse per rev. So that's what this 36 minus 1 means. So the black curve is with the 1 pulse per rev, green is with the 36 pulses per rev with one missing pulse. And we can see that when you have the multi-pulses per rev, you can see a lot more dynamic content in the signal. So it captures the variation in the RPM in a more detailed way compared to the 1 pulse per rev. And that type of detail is important when you are transforming the data from time domain to angle domain. And that is why we should try to make sure that we can get as many pulses per rev as possible.
And just so I understand, Raj.
Yep. In this particular case, the engine was actually combusting. This particular cylinder may not be combusting, but the other cylinders were combusting.
Okay, but so this one had a proximity probe, and this is just one method to try and determine precisely the top dead center. There's
correct.
Other methods with non-combusting engines where you look at like the pressure, but here we're looking at the distance from in this proximity probe that was installed in one of the cylinders.
That is correct, Pete. Yeah.
Okay. But when they go to run the engine to do the combustion analysis, they'd probably take that probe out and then have that cylinder operate normally. Otherwise, it's...
Yes, correct, Pete. Yeah, in this particular case, we are using the proximity probe sensor signal for the top dead center determination, yes. We see that there is this proximity probe, and then there is 1 pulse per rev signal, and then we have the multi-pulses per rev. And these here, these are this raw and the raw reference, they correspond to what are called as tacho moments. They are the moments in time at which the pulse crossing occurred, and they are captured also. And those will have the information about exactly when the pulse crossing happened. And so we will use that information for the TDC determination. So with that, I'll put this data into our input basket. I'll go to this time data selection worksheet to load that data so we can see those channels. And then I go to this angle domain validation tab, which is where I will be able to set up the parameters for doing the conversion from time domain to angle domain. In this part here, I want to look at, let's say, the RPM trace. I can check that box. And I want to look at this proximity probe signal. I want to see both of them. By default, in this particular module, it shows the data in time domain as well as angle domain. And it has some overview and detail. Because I'm interested in mostly angle, I'm going to uncheck the time domain display. So now what you see here is this RPM signal and this proximity probe sensor signal. The top part is called as the overview, and the bottom part is the detailed view. And the way this angle domain validation worksheet is laid out is we bring the data here, we're able to view the data here, and then we specify the parameters for this time domain to angle domain conversion here in the bottom left hand part here, right? So here what I'm saying is that I specify like the number of cycles per revolution. I specify what is the angular resolution I want. So here I have said I want the data to be resampled to 0.1 degree angular increment, and that produces 3,600 samples per revolution. We have 360 degrees, and we specified the resolution to be 0.1 degrees. So that's what resulted in 3,600 samples per revolution. I'll change this reference angle to 0. here so that we are able to see how the data comes. And as a matter of fact, I'm going to uncheck this overview and I'm going to look at only the detailed view.
I thought when you were describing the conversion from time to angle, it might take forever, but this was very quick. You just typed in the numbers and now we're looking at 1/10 of a degree resolution.
That's correct, Pete. That is Testlab software and that is how fast it is. Okay, so here I'm looking at this RPM and you can see there is some fluctuation in the RPM. So that is typically what we would see on a normal engine. Even when it is idling, the RPM fluctuates a little bit. And I have the option here to look in terms of RPM, or I can look at it in terms of the reference pulse, which is the 1 pulse per revolution. I also have the option to look at it in terms of the pulse, which is in this case, the 36 pulses per revolution. Now notice here that
I didn't know that you could flip that little thing from RPM to pulse to see the actual pulses. That's kind of cool.
Yeah, it is indeed cool, because that is really useful information and it is getting that from the tacho movements that we were talking about.
The reference pulse is the single pulse per rev and the other one was the higher pulse per rev. And that's why the one looked denser than the other, huh?
That's correct. That's correct. Yes. So here when we see this, as Pete mentioned, like this is the 1 pulse per revolution. And for a 4-stroke engine, we have 2 revolutions constitute 1 cycle. So per 1 engine cycle, we will have 2 of these pulses. And so we have to figure out a way to use only one of them for the zero referencing. And for that purpose, we can use some a priori or known information to ignore one of these 2 pulses. And here, if we look at it closely, right, we'll see that this proximity probe sensor signal, it doesn't have a constant amplitude. It actually has higher amplitude in one cycle, and the next cycle it reduces in amplitude, and the one after that it increases in amplitude. We have to decide which one to use, which pulse to use, right? So in this case, I know that the one with the lower amplitude for the proximity probe, the one closest to that is the pulse which I have to use. So I have to keep this pulse and I have to ignore this pulse and this pulse. So I have to keep this pulse and the one ignore this pulse, and the one after that I have to keep that again. So we have to specify a logical condition to ignore these unwanted pulses and just use the pulses which are actually relevant to us. Hope that makes sense, Pete.
Yeah, so the little gray line there indicates where it currently thinks TDC is?
That's correct.
0 degree position?
This is the 0 degree position. So the way Testlab works is when pull in the data, it will look at the first pulse and then it will use that for the 0. But in this case,
we wanted to use the next pulse.
That is correct. So this light gray line, that we have to pay attention to that. It may not be obviously visible, but that is where currently the 0 is. But we want the 0 to be here. So let's use these options in this advanced tab here to specify conditions.
Raj, before you do that, if you close.
Yeah.
So Raj, to know what degree mark you're at, you could turn on that cursor on at the top and then it'll actually read out. So that's like cycle 445 and you're at
cycle 0. Cycle 0 and angle is 24.
Oh, cycle 0. You're at cycle 0 and 0.96 degrees.
Yes.
Now you're at exactly 0 degrees. But you can always see what degree mark you're at if you're wondering with the cursor.
Correct.
Okay.
Yeah. So here, so this is currently the 0, but we want to make here to be the 0. Okay, this pulse to be the 0. So we are going to define some condition to be able to do that. And for that, first we have to look at this amplitude level and use that to specify which pulse to be used. So here I'm going to include a white cursor front. It should show like 4 or 5 decimals, because we can see that values are very close amplitudes, that is. So if I move this cursor and put it here, like I can see the level at which this one is at lower. We can say accept this when the proximity probe signal is lower than this value. We will also notice that if we zoom into this area, so we'll see that between this reference pulse and this proximity probe signal, they are, if we further make the selection like this. And if we can look at the values, right, they are about 80 degrees apart, right? So that is some additional information we can provide for it to precisely position itself and to determine the zero reference. So we saw that. Okay, so let me zoom out a little bit. Okay, so I have it here. So here I'm going to say in this advanced tab here, I'm going to conditionally accept this reference pulse with respect to this reference channel, which is this proximity probe signal. And I'm going to say if it is below this value of 4461, I'm going to put that value and I'm going to select absolute level here, 4461. And I say the condition angle, if it is within 80 degrees of that, accept that, around 80 degrees, right? So this is approximately is where to look for it. So if I can click on close, and now if I click on the refresh data and display, now see what happens. Now we see that the zero, it actually corresponds to the pulse that we wanted to take. And it is closer to where this proximity probe amplitude is lower. Previously it was here, but now because of this zero angle definition criterion that we have set here, it is now at this position here. This is how you can specify which pulse to use for the zero referencing purposes. And this is especially important because in a 4-stroke engine where you have 2 revolutions per cycle, you have to eliminate one of these pulses. We have placed this cursor, and this cursor, as we move this cursor, we can see that the angular position indicated by this bottom part here, it will change. And in this cursor, the way it works is, like if you double click on it, you will see that there is this 0:0.64. So that means it is the 0th cycle and 0.64 degrees in that cycle. And if I move close to here, then we will see that at this peak, it will be close to that 80 degrees. That is where we thought this reference should be. So that is where it is specifying it to be. So that is how this cursor works, and you can see that it found it correctly. But basis for determination of this zero referencing, it is using only the first cycle, not all the cycles or not several cycles. So that is where you can use this TDC determination option in the combustion analysis to use multiple cycles to determine the TDC position in a more statistical way.
So in angle domain validation, we've only done it for one cycle.
Yes, correct.
In the combustion analysis, there's even something further which looks at the statistical spread from cycle to cycle.
Yes. So with that, let's go to this combustion analysis. And on the top left-hand side, you will see that there is a TDC zero angle. If we click on that, then that gives us the option for specifying the parameters for this more precise TDC determination. As I mentioned previously, TDC determination is very critical for combustion metric calculation. If you don't do that correctly, then you can get a lot of wrong answers. So you have to pay a lot of attention in terms of the TDC determination. So in this, when we click on that button, it opened this window. And in that, now if I click on this load channels, I have the option, then I'll see that all these options become activated. Because I know that the data for this particular scenario for which we are determining the TDC is coming from a proximity probe, I'm going to select this proximity probe option here. And I'm selecting the reference channel as the voltage signal from the proximity probe. And I can use number of cycles to determine this TDC. So I can specify the number of cycles I want to use. Here in this case, I have said 50 cycles I want to use. And then I can click on this calculate TDC button to do this calculation. So I'll click on that. Once I do that, it is using not just the first cycle, but 50 cycles to give me a good statistical estimate for this reference angle. And there it found it. And it found that the mean value, it is negative 78.51 degrees. So that is what we should use for this combustion analysis TDC determination.
Not quite 80 degrees. Standard deviation is very small.
That's an excellent point there, Pete. It is not 80 degrees. If we had just eyeballed it or just thought that that is going to be the value, no, that is not right. We are going to be off by 1.5 degrees, which is really huge when we are trying to do the combustion metric calculation. And we can see that within this 50 cycles, the determination of the TDC the standard deviation from among the 50 cycles is 0.06 degrees. So we are very precise in terms of the definition of this reference angle. So once we have done that, once we have calculated that, then we can use that for processing.
And Raj, if I was only doing combustion noise analysis, maybe that would be fine, right? Using the 80. But if I'm going to try and do combustion metrics like IMEP, NEMEP, etc., then this is very important.
Yeah, yes, that is correct. For the combustion noise, the definition of the cycle is very important. So we want to make sure that one complete cycle is captured. The location of the TDC itself is not so critical for combustion noise purpose.
And combustion noise is just that little checkbox over on the right.
Yes, correct. So once we have determined that, you can click on this use for processing button, and that puts the value back in this angle domain validation worksheet. And now if we see, if you do the refresh data and display, select that area and zoom in. Now if you place it at 0, the cursor at 0, then we'll see that that is exactly at 0 degrees. This is based on the statistical estimate. So we are very confident with that particular calculation and the precise placement. So this is one way of determining this TDC. So I'm going to put the parameters back here. I want to show the next method for using the TDC determination. That is using a motoring trace. A motoring trace is when there is no combustion happening and you are just cranking the engine so that the cylinder pressure increases gradually or in a more controlled way, I guess. And you will see that the cylinder pressure itself is very consistent in that case. There is no variation from cycle to cycle. Unlike that proximity probe sensor where the engine was actually running, where you can see the fluctuation, but here it is absolutely constant. Do you see that, Pete?
Yeah, so in this case, we're using an engine that has no combustion to determine the TDC. Again, you may not have to do this if you knew your TDC for your own engine. Might be an engine you don't know the TDC for, and then they just like hand crank or they use the starter to move it along without actually running the engine on. And that's why the pressures are consistent.
Yeah. So in this particular case, we can use another method that can be used for determining the TDC. Let's take a look at how to do that. Okay, so I'm going to put this data in the input basket, and I go back here and I will replace old data with this new data. And I go back to the angle domain validation worksheet. Now I see that I have the RPM and also I have the cylinder pressure. By default, I'm looking at it in the angle only. The view here, view alpha or the view angle shows directly the data in the angle domain. And like previously, I want to see the reference pulse, and I got it here. I'm going to move the cursor so that we can see where it put this 0 by default. In this case,
but 0 should be at that pressure peak.
For TDC, yes, we want there to be at position.
All right.
And we will see that even here, there is this pulse. We don't want to use this pulse. We want to use this pulse. Again, we can use this 0 angle definition, some other criterion to determine which one we want to use. So I can say conditionally accept reference pulse based on the pressure above and a relative value of 50% over the maximum cylinder pressure over this reference value. What this means is that it will take the pulse which is closest to where the cylinder pressure is more than 50% of its maximum and within this condition angle of 80 degrees. We saw from the previous that between this pulse to the max value of the cylinder pressure, it is 80 degrees. Now, it so happened that this data was already correctly referenced. So that's why we don't see the shift in here. But if placed here, then it will take this one starting. Now, when we use this motoring trace, the motored cylinder pressure trace, in the TDC determination, 0 angle, we can choose another option for that. So again, I'll go to load channels. And this time, instead of proximity probe, I select the max pressure option. In the max pressure option, I want to use this cylinder 1 pressure for the reference purpose. And now you see this option called pegging. Pegging is very important to do to remove the drift in cylinder pressure signal. You know, this cylinder pressure sensor is placed in the combustion chamber and it is exposed to very high temperature. And this is piezoelectric sensor, and its value drifts over time. And so even from one cycle to the next cycle, the drift can be different. And so you have to correct for that drift. And that is what you do in pegging. You correct for that drift.
This is a drift or an offset on the amplitude of the pressure.
Yes, correct. This pegging can be done in different ways through a reference value. Like you can say, hey, this is what the pressure should be at this angular position. You can do that. Or using a reference channel, for example, from measuring from an intake manifold pressure. And you can say when the intake valve opens, the intake manifold pressure should be actually be equal to the cylinder pressure. You need to do the intake reference channel measurement in that case. Or the other option is used to use this polytropic coefficient method. This polytropic coefficient, it is based on the fact that for the combustion, the thermodynamic law PV to the power of gamma is equal to constant. That law has to be satisfied all the time. And so during the compression stroke, we will see that the slope of the line should correspond to the slope of the PV to the power of gamma curve. So knowing the polytropic coefficient and between what certain range of angles that you can provide, where that should be constant value, then you can use that information to do this pegging. That is to correct for the offset or the drift. And then again, we will do calculation over 50 cycles. When I hit this calculate TDC, now for this particular trace, it will determine what is the reference angle should be. You can see it found out to be negative 79.12 degrees. So it calculated based on this 50 cycles, and the standard deviation is also very low, 0.04 degrees. That's very good. And if you want, we can use this for processing. And when we click on that, I'll close this. And then I go to this angle domain validation worksheet. Now we see this is at negative 79.12. Right now the cursor is at 0 degrees on the pulse, but if I apply this, then the 0 degrees will actually be at the peak of the cylinder pressure. And this is based on a statistical estimate. So we have good confidence in this way of determining the TDC.
TDC means the piston is at its highest point in the cylinder, hence the word top dead center.
Yeah.
And therefore the pressure needs to be max on a non-combusting engine. But on an engine that has combustion, the pressure max might not be the position of TDC because they're firing, sparking before it reaches TDC and things like that.
Yes, a very good point, Pete. In a non-combusting engine, the TDC will correspond to the maximum cylinder pressure, but when combustion is happening, the TDC will not correspond to the maximum cylinder pressure. If you want to see more description of what is pegging and how it works, we can click on this help in Testlab. So in combustion analysis, on the top right-hand side, you see a question mark there. So if you click on that, it opened up a new window in my other monitor. So I'm going to bring it here. It actually goes through what this module does and how to set it up. It have very good descriptions of the different options there. Okay, so that is one more demo we completed. Once we have done this TDC determination, then the next step is actually the calculation of this combustion metrics. And in this combustion analysis tool, you will see that there is a lot of different metrics that can be calculated. The indicated mean effective pressure, the pumping mean effective pressure, net mean effective pressure, peak pressure, the angle of peak pressure. Peak pressure is within a cycle, what is the maximum and what is the angle at which the maximum occurs. And it also calculates the pressure rise rate, peak pressure rise rate, PPPR, and the angle at which this occurs. So all these are available to be calculated. And in our case, we can also calculate combustion noise also. That is a checkbox here. Now, what is combustion noise?
Before you do that, just so I'm clear, you are doing the motored example to determine TDC. Obviously, at this point, we need a recording where there's actually combustion occurring in order to calculate the combustion. So you have to switch data sets at some point here.
Yes, I'm coming to that. So in this combustion analysis, all these metrics are available for doing this calculation. In addition, there is this option for this combustion noise, where we want to determine what is the radiated noise from this combustion event inside the cylinder. We can also look at definition of combustion noise and how it is calculated in our help also. So this is what the combustion noise. So we take the cylinder pressure trace, and we do the FFT of the cylinder pressure trace, and we actually divide by this structural attenuation function. That structural attenuation function is called the Lucas transfer function or a Lucas meter structural function, because many years ago it was found by Lucas that the sound radiated from the engine based on the cylinder pressure is actually a transfer function for that. He measured the cylinder pressure, and also at 1 meter away from the engine he measured the microphone noise. Now over the years it has been determined that this structural attenuation function changes in amplitude a little bit for different engines, but the shape of it is fairly constant.
That's a transfer function that is pressure over pressure, pressure inside the cylinder versus pressure 1 meter from the engine.
Yes, correct. And once you have multiplied that, you can calculate the RMS value to determine the combustion noise. Because, as I said, like this structural attenuation function may be specific to your own engine, and if you have that attenuation function, you can load that here. And by default, we provide one, but if you like to use your own, you have the option to do that also.
Were you going to show us that transfer function?
Yes. Okay. So in this case, I have plotted that transfer function, and this is how it looks like. It is defined in terms of the octaves. The cylinder pressure is divided by this function here.
Yeah, so low frequencies will be less, high frequencies will be less in the end, kind of like the A weighting curve of the human ear.
Right. Low frequencies will be attenuated more. Is that what you mean, Pete?
Low will be attenuated and high will be attenuated.
That's correct. Yes, compared to the mid frequency range. Right. Yes, exactly. So,
the inverse of the A weighting curve, I should say.
Right. Yeah. Okay. We see all these calculations, the options available. So let's see with some real life example data how to make use of that. I have some example data here. So let me change sections here. I'm going to go to this combustion analysis 4-cylinder run-up. And I go here. I have this data in this throughput file. This is 4-cylinder, 4-stroke engine, right? So the 4 cylinders, I can see that. And I have a tacho channel. It has multi-pulse per rev as well as one reference pulse per rev. So let's take a look at this cylinder pressure. So if we see that, or first, actually, let me look at the tacho, right, to see what data that I have. So in this case, what we have is an RPM trace for the tacho. We can see that it's going from about 2000 RPM to 6000 RPM. Initially, it is fairly steady, but then after that, the RPM is increasing, and then there is a rundown where the RPM decreases. As you can see, the x-axis here is actually time. So this data is originally acquired as a function of time with a fixed sampling rate. Because this data is in time and the RPM is actually changing, it is important that you would transform the data and do the resampling to angle domain, because the time taken for each cycle will change as a function of this RPM. At low RPM, the time for each cycle will be higher compared to a high RPM. But if you transform the data to the angle domain, you will be looking at the data from cycle to cycle basis. So you will not be constrained by the variation in the RPM. You will be looking in terms of the angular position and in terms of the cycle. Now, if you take a look at the cylinder pressure, so this is how it looks. I'll change the format to real. And in the cylinder pressure, as we saw earlier, like, the RPM is changing, not so much initially, but then after that, it's a run-up going from 2000 to 6000 RPM. You can also kind of see the drift in the cylinder pressure. So we need to correct for that, and that is done through pegging. So that is why you can clearly see that there is an effect of the drift, and that is something which you have to keep in mind when you're doing the calculation for the combustion metric. So this is the situation where there is actual combustion event happening. So in the previous examples we saw, like in the motoring trace, certainly there was no combustion, and in the proximity probe case, there was combustion, but we are not capturing that. Or actually, in the spark plug was removed by the proximity probe, so that particular cylinder in which we are capturing the proximity probe data, it was not combusting. So now we have the real combustion data. So let's see how we can utilize this data for doing this processing in the combustion analysis. So what is the first thing we should do, Pete, when we are doing the combustion analysis? What do we want to make sure?
Select the time data, make sure you have good TDC and cycle definition. Also make sure the cylinder offsets are entered.
Wow, okay. That's very
Or
good.
did I
Very
go?
good. No. You captured everything, Pete. So as Pete said, TDC determination is one of the critical steps. In this particular case, we would have liked to have the data for the TDC determination. We would have gone through the process of motoring or the proximity probe. For this particular data set, unfortunately, we didn't have that, but we knew that the reference angle is at negative 110 degrees. So we know that, and that we can specify here in the bottom left-hand side.
I like just knowing it. It's a lot less work.
Yeah, it certainly is.
And in this, don't you have to scroll over to do some cylinder offsets?
Yes, that's an important point here. By default, when we look at the data, if we go back to look at the data in time, to remove this curve here, if we look at cylinder 2, so we'll see that I'm going to bring cylinder 3 and cylinder 4. Okay, if we look at the cylinder pressure traces from these different cylinders, we will see that they're not aligned, meaning that the maximum pressure doesn't occur at the same time because there is a certain order in which they fire. And for a 4-cylinder engine, it is 1, 3, 4, 2. 1, 3, 4, 2. So first the first cylinder fires, and the next will be the third cylinder, then the fourth cylinder, and then the second cylinder. So 1, 3, 4, 2. Right? That is the order in it. So they're not all happening at the same time. They happen one after the other. Knowing this information, we have to specify that cylinder offset. We have to use this cylinder offset column to specify that offset. So,
and if you view those, then they'll be aligned.
Right. So if we view them now with respect to this angle, now we will
Maybe
see
have
that
to overlay them under options.
Yeah.
And then you get to pick them again.
Yeah. Now you can see that the 4 cylinders, instead of being not aligned, they're on top of each other because we specified this cylinder offset here. If we zoom in here, we'll notice that even within this, for one cycle, the cylinder pressures are not exactly the same. And that is why we want to look at each cylinder's performance. Here, once we have specified this cylinder alignment, cylinder offset, and we have aligned the cylinder pressures, now we are ready to do some further analysis on that. As we had discussed before, I'm going to put this reference pulse here so that I can see. And in this particular case, we know that the reference angle is at negative 110 degrees. So I'm going to refresh the data and the display, right? We can see that the 0 degrees is close to the peak cylinder pressure, but not exactly at that. When there is no combustion event, we expect this is where the peak cylinder pressure to occur. But when it is not that, you will see that most commonly it will be after the top dead center. So we specified that, and then we say now use this data for processing. And we go to do this combustion analysis, and we'll see that those parameters have been copied over from there and use these for the processing. I have the option to look at drag as a function of angle. I want to see how, from a cycle to cycle basis, how is the various combustion metrics that I'm interested in, how they are changing. And I specified the duration here to be 100 cycles. So that means that it will look at the first 100 cycles of data. As we saw, the cylinder pressure was actually, there is a drift in that. So we are going to do the pegging using the polytropic coefficient method. And for this polytropic coefficient, the exponent is 1.33, the PV to the power of gamma, that gamma is 1.33. And I want to use this reference angles to determine the slope in the PV diagram to do the calculation. Once I specify all these parameters and I can check all the boxes for which I want all the calculations to be made, then I can click on this apply and calculate button to do the calculation. When we do this apply and calculate, that is when it applies all this formula in the time data processing worksheet. And that is where all the formula are written using these parameters that we specify. And it does the processing. We see the progress bar, and then we have to wait also here at the bottom part of it to see how much it has progressed. And it's saying converting angle domain to throughput, because that is one more step we are doing. The waterfall data that is generated from the different cycles, that we are converted into angle domain derived throughput as a continuous stream, like a time history trace. So that is done. Then we get this message, processing is finished. So now I'm ready to look at the data. So as I was saying, when we hit this apply and calculate button, the formula required for all these calculations are applied in this user sections AD. And this is how to do the pegging and how to do the calculations for the maximum pressure and doing the calculation for the angle at which the maximum occurs. All those calculations are shown here. And it applied these formula based on the parameters we set up in this tab here. And after this is done, then we can go to the navigator and we'll see that this is the latest result that has been computed. And I can go here and I can look at the result. There is a lot of different things we calculated, and let's take a look at the result. So originally we have this cylinder pressure trace. Let's see if I pick this 25th cycle here, and I'm going to plot it here. I change the format to real. So this is the original cylinder pressure trace. Here you see that there is a waterfall, and because we analyze the first 100 cycles, we have 101 curves in this waterfall, and we can look at each of the individual cycles for this cylinder 1. So this is the original trace, and then if we want to look at the pegged cylinder pressure trace for the cylinder 1, and I will bring the same 25th cycle, then we'll see that this is the pegged trace, the green curve. So it applied the pegging or the offset or drift correction to move it from here to here.
Yeah, the flat area is a lot closer to 0, huh?
Yes, correct. It's a lot closer to 0. The best way of confirming this is actually by looking at the data in the PV diagram. We'll take a look at that. And then you will see that there is a lot of different curves and metrics and waterfalls that are calculated. You will see that one of the waterfalls is the combustion noise. It generates a spectrum for each cycle on the pegged cylinder pressure trace. So if you want to take a look at that, I'm going to generate like a color map, and I'm going to drag and drop it into this display here, and I'll change the format to dB, and I'll change the unit to Pascal. So this is in terms of octaves, it is showing, and I can change this to octaves, format octaves, okay, and I can change this value to access to cycle. So what we are seeing here is how is that combustion noise spectrum changing from cycle to cycle as a function of frequency. So there you have the combustion noise along with the other metrics that you calculate. Okay, and this is for one cylinder. Similarly, we can look at the data from other cylinders and such. And here we also have this combustion metrics that are calculated, but there is a lot of other things too. IMAP, PMAP, NMAP, and they are all computed on a cycle by cycle basis. If you look at IMAP, this is on the pegged cylinder pressure, and typically I will look at it in terms of bar. So this is how it was changing: IMAP, then PMAP, and then for and NMAP. X-axis is shown as angle, but you can change the axis to show in terms of unit, to show in terms of cycle. So what we see here is how is this different combustion metrics for the cylinder 1 is changing as a function of this cycle. So we processed 100 cycles, so this is how it was changing. You can see all the different metrics are calculated, and they are nicely summarized here so that we can take a look at them and make decisions for our design changes. And we'll also see that there is a throughput derived. So the original throughput data is there, but then now we have throughput derived. So if you want to look at the pegged cylinder pressure trace for cylinder 1, I can plot that here, and I change the format to real. This is shown as a function of time, and if you compare that to the original cylinder 1, so the pegging is applied, you can see that. But also here in this green curve, you can see which is the original cylinder pressure trace. There is a drift which is going from left to right, if you see, but that is not there for this black curve, which is the pegged cylinder pressure trace. So the pegging was applied on a cycle by cycle basis, not just for this cylinder, but for other cylinders as well. One of the other major considerations or data quality indicators for this combustion processing, combustion analysis, is the PV diagram. So let's take a look at that. I can do that type of plotting using this CAXY plot. XY plot allows us to plot two independent quantities with respect to each other. So for example, here we have the pressure as a function of angle or volume as a function of angles. But if you want to plot pressure versus volume, then we can use this XY plot to do that. In this combustion analysis tab, there is an option to specify the cylinder geometry. That is where you will enter the various parameters for the geometry of the cylinder, the crank radius, the offset bore length, and all that. Based on that, it computes a certain displacement volume for that cylinder that we are measuring. Once we do that, then it generates this angle cylinder volume curve that is stored in this section. I can plot that angle volume curve and then plot this on this horizontal axis for this here. I plot it there. Let's say like I'm going to use one of those pegged cylinder pressure trays. Previously, I had done some processing on a long trace, so I'm going to use one of those. Let's say I select 250th cycle. I'm going to plot that here. So this is how it looks like. Pressure, volume, PV. Y-axis is pressure and x-axis is volume, pressure volume diagram. One of the key quality indicators in the pressure volume diagram is this area here. You can see that it's fairly flat or it has a constant slope. That is good. That is what we expect to see. This is in the compression stroke, and we expect to see that if we did the TDC determination correctly and we did the pegging, then this is what we want to see. If we compare that with respect to a cylinder which has not been pegged, then if we get the 250th cycle for that, for cylinder 1, it looks like this. Notice that it doesn't look anywhere close to what we expect to see in a typical PV diagram. And in this case, there is no constant slope area here. That is concerning. This green one is the original cylinder pressure, so it was not pegged, and that is why it is producing a result like this. We should always do pegging, and as part of the pegging, you do the TDC determination also. Those are important things to do for combustion analysis. As part of this processing that we had just done, we saw that there is combustion noise was calculated, and we can plot that also on a cycle by cycle basis. Here I am showing it in terms of the dB, and I can capture other cylinders also. So what we see here is that how the combustion noise is changing on a cycle by cycle basis. You can see that it's not constant. It is sometimes going up, going down, and it's varying from cylinder to cylinder. Then you have to understand why it is doing that and what are some things you can do to fix that. I think that is pretty much it, Pete, that I wanted to cover.
That was great, Raj. Thank you.
Okay, good. I want to finally wrap up with some final comments. So in this Simcenter combustion analysis, we saw that we can calculate the various combustion metrics like IMEP, indicated mean effective pressure, net mean effective pressure, and other metrics like combustion noise, simultaneously with other NVH metrics that we are used to, like the overall level, order sections, and all that. Using one system for both the combustion and for regular NVH, that gives us a huge advantage because now we have synchronized data and we are clearly able to understand the cause and effect type of relationships better. Even when we are looking at how things are changing within a cycle, right? Sometimes things may be happening within one cycle, and that is where it is critical to have a lot of pulses per revolution for your angular position measurement, because that gives us insight into whether it is happening during the intake stroke or during the exhaust stroke, even within a cycle. If you have multi-cylinders, a lot of cylinders in your engine, you can capture cylinder pressure from all the cylinders, then you can see how things are changing from cylinder to cylinder. So not just on a cycle by cycle, but from cylinder to cylinder. That can give you some valuable insight for troubleshooting and optimization. For this combustion analysis, one of the critical steps is the top dead center determination. We saw the different methods that are needed for this top dead center determination. They are all available within the Testlab combustion analysis module. And also the pegging. You are bound to have drift in the cylinder pressure signal, and you have to account for that in the combustion metrics calculation. And the pegging schemes, like based on the polytropic coefficient, or using a known reference value, or based on a reference channel that you have measured, all those options are available in combustion analysis module. That's what makes it very unique in terms of the Testlab combustion analysis. You can do all in one package, the standard NVH metrics as well as the combustion metric. Okay, thank you all for attending this webinar.